Hi, my name is Mihai John. I'm a HVAC SME and I'm working for an engineering department. I'm doing this video so I can show the reason behind the airflow distribution control errors and the related side effects. What you see here, this is our AHUs, the way we run them. We have the AHU, then we have the extracted air. We have ducts, which allows us to direct the air where we want, and the air is directed into the rooms. Also, then we extract the air using the extractor fan, and part of the air is recirculated and part of the air is exhausted. We have the fresh air intake, and it looks pretty simple. Now we have the AHU, which circulate and process the air. We have ducts which guide the air to the required area. We have dampers which controls the airflow. Coils controls the air temperature and humidity. Actuators control the dampers and the valve's position, which allows more or less glycol or steam to pass by to the heat exchanger when we control the air temperature and humidity. Probes which collect data from the duct or from the pipes and send data to the programmable logic control. Also have the programmable logic control, which have a software inside based on a control philosophy, which controls the AHU's capacity and send data to the SCADA to be trended. If you look a little bit deeper into the AHU, it doesn't look as simple as we think it is. We have a lot of control equipment like differential pressure modules, differential pressure control, velocity probes, humidity probes, temperature probes, and we really have to look into all these probes to maintain them properly, and they're a lot. You'll also see how the air circulates through this AHU. You can see we bring some fresh air, also with recirculate a quantity of air. The recirculated air meets with the fresh air intake, and it goes via the supply air chamber. It pushed into the duct and it goes into the room. And we'll also have dampers, which allows us to decide the quantity of air we want to exhaust or to recirculate, or how much fresh air we have to bring inside the rooms. And because of the room's problems, the system is completely unbalanced, and I'll explain to you how this is working. Our system uses a Siemens PLC. People call him CMR, but this is a Siemens programmable logic control. The system is designed by CMR and SHP lately. And this is the human machine interface, which mirrors the AHU, so we can monitor the set points, the air velocity, the temperature and humidity. We can collect data, and data will be sent to SCADA where it's trended, so allows us to do some analysis and decide if the unit, if the AHU runs well or not. AHU is just a name. We have fan motors, variable speed drivers. So the air handling unit, it is not just a box, it's got multiple parts inside, which helps us to move the air and also to condition the air to deliver the required capacity for the demands. If we don't know the room heat loads, we wouldn't know what type of AHU we want to use, and I will go deeper with this explanation in a minute. Another important thing it is the air handling unit control philosophy should be written by a HVAC specialist, and the control philosophy will be communicated to software engineer, which will apply the software philosophy in the software, the control philosophy into the software, and then the HVAC specialist will test the AHU's function to see if there's any glitch into the control philosophy or into the software algorithm which runs the unit. Unfortunately and painfully, I have to say that in the past people look like Superman. They calibrate DPMs and DPCs with the speed of light. Probably they need a ceramic shield not to burn their face in the friction with the air. The calibration has been done extremely fast, and if you count the steps of the human being against how many calibration has been done per day, you will pull your own conclusion. Now you will see better. This is the type of AHU we use and what we monitor. We have global airflow. You can see here 50 meters per second. There it goes into the many branches which direct the air into the rooms. We extract a quantity of air like 48 meters per second, and we bring 5 meters per second fresh air, and we exhaust 1 meter per second. By looking at the difference between how much air we bring in a building and how much air we exhaust, is clearly visible that we lose 4 meters through the door or building fabric errors. Other issues in the past, I was dealing with problems in 2019 when I've been employed. People have the bad habits to go into the room and to manipulate the dampers which are fitted in the bulkheads, disturbing the air distribution through the room. Like you'll see here, the air takes only one direction because the rest probably of the extractor dampers are either blocked or the dampers are closed. This is something which probably have to be debated with IT. We have the human machine interface, which is password protected. We have the SCADA, which is a password protected. We have the client, which is password protected. The PLC supposed to be secured, but anyone with laptop can plug into the PLC and change the set points. The PLC is not passworded, and the variable speed drivers also don't have any passwords. Someone can go to change the software of the variable speed drivers. We have a lot of back doors. We have differential pressure controls, which are electronic controls like microcomputers. People can change the set points, they're not protected. We have valves which can be manually manipulated, and there's nothing to capture their position, they're not trended. So we have a lot of problems with our control equipment. From let's say, I'm not sure, legal point of view, or I'm not sure what's the IT view about this, or engineering, but from my perspective I have a lot of backdoors and people can manipulate data, and I wouldn't even have a clue what has been done. And with many occasions I have to stay hours either here in Kedron or at home to figure out what happened to a system and how to bring it back to its working state. You have a better view about the AHUs. What we have here, we have pitot tubes inside the duct, and these pitot tubes will only send the airflow data to the SCADA. I pull a conclusion that if I will use a T onto these tubes, which comes from the pitot tubes, I can send data to another DPM, which could send data to the Pharma graph. So then I have a legitimate monitoring to the global airflow and to the air return. So I will know that the quantity of the airflow pushed into these branches will cover the required quantity of airflow to comply with the change rates into these rooms. The only things we worry, the only things we worry is the distribution, because the dampers are manual. Anything happen to the damper can disturb the change rates in a room, so we wouldn't have a clue, because on many occasions I observed that if something happened to an air supply damper, the people will adjust the return, increasing the pressure into the room. People use the pressure difference to figure out if the change rates has been changed, which is highly incorrect, because if someone will restrict the air which is extracted from the room, the cascade can be perfect with an incorrect air change rates, and we check the air change rates only once per year or twice per year on a sterile area. It's very clear here, the fresh air which comes inside the AHU passes by through the frost coil, which it's used to protect the equipment when the temperature outside goes below zero. Then we have the pre-cooling coil, which is the fresh air conditioner, and then it immediately circulated air, and both goes through the main cooling coil, which technically is supposed to be only a trimmer, then to the main heat exchanger, then the humidifier, and then it goes through the airflow main duct into these branches, and it goes into the room. If the heat load is not perfectly calculated into these rooms here, we have a problem, because the air have the same temperature in the duct. So with some occasion we have to put extra boosters or reheaters inline in the duct. Now let's understand better how the human machine interface is looking into the sterile area pressure control, room pressure control. So I have the global airflow, and then the air goes into these two branches which have automatic dampers, and these automatic dampers are controlled by differential pressure controls. The differential pressure control is connected via an air tube to a pitot tube, which uses the dynamic and static pressure to calculate the velocity, and by using a little simple math, by considering the area of the duct and the velocity, we can see how many cubic meters per second or per hour we push into the room. But the game is not finishing here. This differential pressure control converts the pressure into an electrical system which is 0 to 10 volts. That goes into Siemens, which have to be correctly programmed, scaled and normalized. And this data goes into the HMI, where I can see the values. This was a satellite system which was not visible on any AHU. So the mistake that has been done in the past is that if there's any malfunction on this satellite system, which was unknown by new engineers, because the explanation when you get employees is not very clear. So this satellite system will oppose to the global airflow. So the engineers always force the AHU, but these dampers opposed to the global airflow, because they were looking for their old set points. And when I discovered this, there are about 60 dampers which have to be checked and tested, and this system should be connected to the SCADA, so we have a visibility. And this is a project I just did because I didn't want to disturb my work at BPL. We did a project at home. I write the control philosophy, and I asked SHP to help me. So we have an internal test specification, and we want to put this system on SCADA, and we create visibility for this invisible system that run for years in Kedron. Now we'll see better. Inside the duct we have pitot tubes which are connected to the DPC. The DPC controls the actuator accordingly to the set point and then send data to the PLC. When we do the calibration, we disconnect the pitot tubes, we use a calibrated tool, and then we read the data on the calibrated tool onto this DPM, and the data is sent to the PLC, and we can read this data onto the HMI. My idea was to verify after the calibration the system and to use a calibrated tool and to compare the data between the calibrated tool and the DPM while the fan is running to see. This is a verification after the calibration, and then the system have to be validated. So that never happened, unfortunately. Like you'll see here now, when the tubes are disconnected, we have a problem. The calibrated tool shows a value and the DPC shows the correct value. Data sent to this PLC, and on the front end panel we see the same value. And this is wonderful because we have X equal Y equals Z. So all these three shows the same value, which means the calibration is great. But I don't know the condition of the pitot tubes, and that's never been done. As a result of this, I decide that after the calibration, a pitot tube tool must be used, and then we have to verify if, with the system running, if the value we read on a calibrated tool is the same with the value onto the DPC. And I don't care about the PLC too much because we already checked this is calibrated, but I want to see if the pitot tube send the correct pressure to the DPC, because this is the part we never look into it for probably, I don't know, 20 years or whatever. Speaking about the Pharma have again using a CMR DPM. People are confused. They said we calibrate FEMS. We don't calibrate FEMS. We calibrate the CMR differential pressure module, and we disconnect these tubes. We use a calibrated tool, but we don't know about the room's condition, the tube's condition, so the system is not verified or validated. Another issue I struggled with when I've been employed in 2019, I asked about door control philosophy, the door usage strategy, and I explained that even if the cascade is correct, if we have excessive leak from one room to another, we bring not only the air, but we bring moisture and temperature with the air. We bring energy, we reduce energy, and we create a fight between extractor and supply fan. Each AHU fight against each other, and then that will increase the energy consumption, which, through my opinion, at the moment runs at least 20% over. So by balancing the building correctly, we can save about 20% of the energy. Another problem I found is when engineers were going into the rooms, they tried to balance the rooms. The easiest way was to go inside the room and to block the dampers in the bulkheads, but you will see here the air distribution into the room, it is already compromised, and this is a dead area. So in this area we can have fungus and whatever. Even if we have a global air change rate 20 as it should, this area is a dead area because we don't have the correct flow. That was an incorrect approach. I have a chat with my superior at the time, and I go through many conflicts because of this severe investigation I do. Other problems, if we have only one sensor in a room, the validated documents probably should state that this is the highest corner of the room and is deemed to be the reference point for the entire room. Because when I check the room 323, near the room 325, where the door is, I have about 16 degrees, while in the furthest corner I have 5 degrees because I have air leak from 325 directly into this sensor, and I have a false information. If I have two sensors, I could read the average, but if I have only one sensor, it doesn't mean the entire room has this temperature, and this is debatable. I want to make sure that if this corner it is deemed to be the reference point for the entire room, then we have to change the ducts and we have to change the outlets to compensate for the hot air which comes from the other room. This is very important. Now I made this big picture to explain. We have the tube pushes air. Now we have a supply tube that goes into the DPM. Also we have a return, an extracted air tube which goes into the DPM, and we only read the pressure, we don't read the airflow. This is maybe correct for the rooms because the DPM read the pressure difference into these rooms, but reading the pressure into the AHU ducts is highly irrelevant. It doesn't help me with anything because as an engineer I already have this information on a SCADA, so I'm not interested about the pressure to read the pressure on FEMS. It would be good if on FEMS I could read the air volume, because that would be related to the air change rates into these rooms, so we duplicate some information. Now I'll explain a little bit clearer. This is our supply air chamber. We have a fan, and then we have air supply duct branches. Now we can read the global airflow, but we know nothing about the distribution. We have dampers, manual dampers, and they're not properly controlled, monitored, and everybody in the service floor can change, or might have an internal bleeding because they're 30 years old. We don't know how much air passes by through these ducts. We don't. We do once per year. We use a bolometer and we check the outlets where the air goes out into the rooms, and that's it. Something happened within that time. We don't know. Some units have automatic dampers where I can read the global airflow. Also, I can read the airflow in the branches which goes into the room. This is a better system. Use a pitot tube, as I explained before, sending the data to these DPMs, and then the DPM control the quantity of air which passes by, but they validate it to be put on a manual mode. So I can use the automatic function only when I'm balancing the system on a shutdown. Then it's not really helpful anyway. This system has been connected to an ET200 programmable logic control, and I could see this information on Siemens. This is the satellite system I talked about earlier, but I'm not training the data. So I want to do some changing. I can see the value, but there's no trend yet. I can't see anything. And I thought about this about probably around December, and I make an experiment. We build a tool with SHP, and we introduce a Pharma guard server with a Pharma guard trace. So what is this for? This Pharma guard trace have the capability to show me the damper's position, the set point, and the airflow into a duct. Also, I can trend the data for about 10 years, and you'll see this trend looks perfect. I'm choosing as an example AHU 200 room P223. I have the feedback from the damper, which is 20%. I have the set point, which is 4,700 meter cubes per hour, and also I have the sensor, which shows me 4,700 meter cubes per hour. And this is good. This is good. There's nothing I have to do. This is a perfect situation. But if under some circumstances someone manipulate the damper, put the damper on manual mode and manipulate it, I could see exactly the time, which is 20 on let's say it's 20 on April 2024 at 10 p.m. someone put the damper on manual mode, and instead to have 4,700 meter cubes per hour, I have 7,000 meter cubes per hour, and the damper is open 100%. I know exactly the time when it happened. The entire system, it is compromised because look, the pressure dropped. The global airflow looks for the quantity, but the pressure dropped. When the pressure dropped, the other dampers also lost airflow because they set up to be on manual mode. They cannot compensate. So if someone will act on one damper, the other ones cannot compensate. They remain fixed. But I can capture the time when this damper has been, when this damper position has been changed. Then I can question why it's been done like this, or who we can investigate this. Another situation would be a damper failure. This is the most important. Can you imagine a damper failure inside? The shaft shows the same position, 25%. The set point is 4,700 meter cubes per hour, but the value of the airflow is 7,000 meter cubes per hour, which means something happened inside. I can have an internal bleeding, the flaps will collapse. So we can have an internal damage of the damper, which allows more air to pass by. Also, again, we compromise the airflow into other branches, and also we can see the pressure drop. But we see the shaft hasn't been changed, which tells us we have an internal problem, internal bleeding. So the system at the moment shows what it is. If I have the proper support, I can create an algorithm which this system will have the capability to cross-reference all the data and to give you a perfect root cause analysis instantly, and that will happen in less than 1 second. In case if someone changed the set point, there will be a password onto this Pharma trace equipment which will trigger an alarm. The set point has been changed. So now to change the set point, we need a change control. System have to be validated, QA have to be aware. So someone changed the set point, then we'll have an alarm, and someone will have the alarm once we'll have all the documents in place, and this new set point will be approved. Someone will log into the password and will accept the new set point, and then we have a new set point, and instead 1900 instead 1900 we'll have 20,900 meters. So we'll increase the global airflow because we increase the set point if we need more air. So this is about the airflow distribution and the problem I'm experiencing with the AHUs. This is how the Pharma graph look in the real world. You can see the red line, it is the set point. The blue one is the sensor because you have a bit of variation, and the blue one is the damper's position. To see it clearer, you see here I put a date on like 2025 March on 26 at 4:25:29. The sensor shows me this value, 1963 meter cubes per hour. I want to see the set point. The set point is 1950, which is alright, it's almost similar, we have this variation. And also I want to see the damper, it's 42%, it hasn't been changed for a long time. You can see this. This is the beauty of this system. And let's move on. Just eliminates the errors and to help our engineers to understand better how this works. Let me put this one, make it a bit bigger. I want our engineers to understand better how the AHU works. I designed this page, which I'm talking to a software engineer to apply it on SCADA. We have the supply fan, supply duct pressure, supply volume, extractor fans, return. All this is one page, and if all happen, you'll have the fault on red if the damper collapse, or if I have something which is not like as per set point. And then you can press the room cluster, and then you can see what room has been affected by this failure. So you can see anything here. Everything that will get a fault will be on red, and the engineer obviously will investigate the AHU, but instantly you can see what rooms will be affected. Unfortunately, I have to say this was a wrong project. We have some negative pressures in some room. We create fans to extract from the loon shaft. We create a negative pressure, bigger negative pressure, to create a positive pressure by increasing the negative pressure on some areas. So we have a pressure difference which is positive by decreasing the pressures in some areas. So now part of the building, it is a subatmospheric vehicle. Subatmospheric, I can't say submarine, but subatmospheric. In 2020, I calculate the entire airflow and the entire airflow loss to the building. I submit this to where I'm supposed to submit it. I found it in a rubbish bin, my project, and it's been ripped off the wall. Upset some people. If you see here, the fresh air intake, it is 112,969 cubic meter per hour. I'm exhausting 77,148, and the difference 35,821 is what we lose through the doors. So 30% of the air goes in a building we cannot identify. This is where we lose the energy. FEMS tells me nothing if you look to, so I'm using FEMS question marks. You see, tells me, doesn't help me too much. I use the validated documents to check the meters cubes per hour. It's like a CAT measurement against the SCADA, and even if I've been told in the past SCADA is not validated, SCADA is the one that provides the airflow. FEMS reads it, but in my case read nothing, and we have here the errors between these readings. Can you imagine? Everything on red represents an error. Because I like to deal with causes, not with the effects. When we do root cause analysis, we have to understand the causes, what create issues. In this example, you will see here, I'm not sure if you see it very clear, but I have room P215, P246, P215A, and P246A, where the tunnels create a lot of problem. And because FEM looks only to the pressure difference between the rooms, I create a system in which all these rooms are related to the atmospheric, and the difference is calculated after. And I'll explain to you how it works. At this stage, you see how the room behaves against the atmospheric. Like I have a sun to turn the planet. I have a reference point. FEM doesn't, but this system does. You will observe very carefully the reason why the bottom line you'll see here with the blue, which is P215A to 246, went down to -20. We'll try to figure out why. If you look very careful, the black line, which is P215, went very high to one point, and P246 follows it because the SOP said I have to have 25 plus minus 10. So 246 behaves all right. 215 was the cause. And if you see here, the 246 was above 215A, which is steady, and the pressure difference has been inverted. So the cause was 215. Why the pressure went so high on 215? 99% of the cases in the past 10 years, 246 has been investigated, and AHU 813, which was a very incorrect approach, extremely incorrect approach. It has nothing to do with the reality. I got more trends here to show you the amount of trends I have to read when I have a fault, to identify the real problem, not to work with effects, but go straight to the cause. And To make sure that I'll be aware if a room gets wrong, I designed this alarm page. With the limit, I have high limit and high limit, or low and low limit. The high limit is a warning, the high, it's already an alarm. So I want to know before the production if something goes wrong, to save the production and to keep the production running and to keep the machine running. The VHP was something I was thinking for a long time. The VHP is not something that human being will decide. If we have to pause the machine every 5 minutes, that's not for human being. This should be an automatic process. That's in the pharmaceutical industry. So I designed this system which in the beginning of the VHP will turn off the AHU, and then when we'll get the right call, and we'll turn on the AHU. The AHU, this system will tell us the status of the units instantly. You cannot miss if there's a fault, because we'll tell you if the VHP sequence is complete in the end. After the VHP is done, if there's any fault, you'll have a red flag, so the engineers cannot miss. If something wrong with the AHU, we will know instantly. This is the VHP trend when human beings are pulsing. You see, I have one probably, I don't know, 7 minutes, 5 minutes, 4 minutes. Human beings are not precise. And this is the pulsing after I created the automatic VHP protocol. It's perfect, it's okay. I also explain that when people call me stating that the AHU is wrong because the room is too hot, I always have to consider the glycol temperature, the glycol delta T, to see if I have enough flow into the glycol, because these heat exchangers depend on the glycol temperature to cool the air. It's not only the AHU, it is the glycol. And if the glycol is not cold enough, I cannot condense the water, I cannot remove the moisture. And this is it. So guys, I hope you understand what problems we have with our handling unit, and it's not as simple as people think it is. So this page will show you how our AHU works. If you look here, I have onto the return, I have negative pressure represented as positive pressure. I identified this 4 years ago. I raised the problem, and if you zoom into, you'll observe that this is positive, but that's supposed to be negative, and this area, this fan should not be called return fan, but extractor fan. I told you I extract the air, part of it I can exhaust it, part of it I can recirculate it. So it's no fan's decision to recirculate or to exhaust, it's the damper's decision. And this should be a negative pressure, that should be a positive pressure. In our system run on duty standby, unfortunately. One fan run, drag the other one, put in incorrect tension on the belts. Duty assist is another type of strategy. Both fans running, one run 70%, the other one run 30%, but the belts are not a stress, and the bearings are not a stress, and the motors are not a stress, and it's a slight tiny energy saving running the system like that. Also, if one fan will fail, the other one will take over instantly. Will not have like this gap we have now. Duty standby, one turn off, and then the other one turn on, and I have a 30 minutes between. So it will be almost instant. You wouldn't even see if one fan collapses. Duty assist, both belts will have the same tension. It's perfect. Duty standby, the belts will be more stress. Another issue I have, factor control 1.5. We all know that factor control, I have to extract less than we push, but because from other rooms into this corridor, I think it's 230 and 200, a lot of air come, I have to run the extractor fan faster than the supply fan, and as you'll see here, I'm extracting 10 meters per second, and coming back to the supply fan, I'm pushing 9.95, like 10 meters per second, and I'm extracting about 10 meters per second, so which means I have a massive leak from other rooms into that corridor, which is not right. This type of analysis. I think this is it. I hope you guys understood what problems I have with the AHU, and I try to sort out the AHU in B27. If someone have any question about this, you'll find me in B17. Thank you.